Okay, now we have in the second hour, we are going to talk about the improving the capacity of the cellular system using two important techniques, which are called the cell splitting and uh, cell sectoring. We have two important two important techniques to improve the capacity of the cellular communication system. Now let's getting start with this lecture. Well, now when cellular service providers, I mean the companies, build their networks are designed to provide coverage the area of the desire with the expectation of possible increase in the population where in the near future. Okay, so we have to expect that the system will grow up. Okay, what do you mean by system grow up? I mean the number of subscribers will be what will be increased. So we have to have ways by which we can increase what we can increase the capacity of the given or pre-installed system. For example, a company may design a cellular network to cover a city of area 1,000 kilometers squared with population of 1 million people today, assuming that 15% of the population will subscribe to their cellular service, or 150,000 people we have. However, to accommodate possible increase in the percentage of the subscriber or some same percentage subscriber but an increase in the population, the network designer may build the network to provide acceptable GOS, for example, for 200,000 users. Such move guarantees that the network will need any expansion for possibly 5 years. Now, in some cases, may be difficult to predict the need for network expansion, or even when the network expansion is predictable, the time for the network expansion arrive. There are several techniques to expand an already existing network or system. To add more capacity, I mean more number of users to a network being built. In the following, we discuss two techniques. Okay, the first one will be the cell splitting. In the cell splitting, really, what we are going to do in cell splitting, we are going to reduce the cell size. Okay, I mean a large cell will be partitioned into smaller cells. Of course, this technique or this operation is called what? Is called cell splitting. Well, now, when we are going to split a cell, again, we have to keep in our mind an important point, which is what? Which is the signal to interference noise ratio. In the previous weeks, we have what? We have talked about the really the SIR of the system and how we are going to, for example, increase the SIR of the system by what? By providing sufficient isolation distance. Now, in this lecture, we are going to talk about the capacity enhancement. Look, but result in expansion of the network capacity because smaller cells cover less area and therefore more cell would be required to cover the whole region, which directly reflects on the network capacity. Of course, when you talk about cell splitting, just as what? Just as using smaller cluster sizes. Well, using smaller cluster size means what? Means we have a large number of say, clusters will be repeated in order to what? In order to provide the same, say, coverage area. Now, using smaller cells really will lead to what? Will lead to increasing the SIR, or the signal to interference noise ratio. But we have some conditions we are going to follow in order to what? In order to perform the operation of cell splitting successfully. Now, this is shown in the following figure, okay? The first figure shows a cell that has reached its capacity and needs to be split, okay? Look, here we have a cluster size again of 7. As you can see, A, B, C, D, E, F, G. This is the system. And the cell A, which is in red, this represents the cell which is saturated or is a congested cell. So we are going to split this cell into smaller cells in order to provide the larger capacity for the system. Look, please. This cell is split into several cells. Since the area of a cell is proportional to R squared. Now, in the first hour, we have talked about the area of hexagon. Do you remember? We said that the area of the hexagon is equal to what? Equal to 2.598 something. Well, just as 2.6, R what? R squared is good. 2.598 R squared. Yes, so reducing the cell radius to the 1/2, okay, to the 1/2. It means that what? It means that R will be replaced by R over 2, okay, R over 2. So R over 2 squared will be R squared over 4. So the radius of the new cell, I mean, which has the radius of R over 2 will be a quarter of the area of the large cell. So theoretically, we can say every one large cell can be what? Can be occupied by 4 smaller cells. Well, so every one congested cell will be what? Will be replaced by 4 smaller cells can fit into one of the large cells. However, since it's not possible, why we have hexagon shape really to fit 4 quarters hexagon cells completely into one full size hexagon cell, some regions will have to be covered by adjacent cells. Okay, this is the idea of what? Of the cell splitting. Okay, keep in your mind the radius of the new cells are behalved. Okay, so the area of each new cell is equal to 1 over 4 the area of what? Of the larger cell. Now, look, we said that practically we can't fit 4 smaller cells into one large cell, so the other areas will be covered by the adjacent cells. Now, note that the following cell splitting, the new small cells are reassigned in new frequencies. Look, as you can see here, at the beginning, we have cell A. By now, we have C, E, G. Why? Look, please. C is far away from what? From this C. Okay, and G is location what? Is far away from what? From the this large G. The same story for what? For E. Again, don't forget that the tower height will be reduced and the power transmitted from the smaller cells will be what? Will be less than the power transmitted from what? From the larger cells. So we will avoid the interference, I mean the co-channel interference. Well, look, please, here we are going to discuss the amount of power transmitted by new cells. Now, that don't cause co-channel interference with adjacent cells as shown in the above figure. Okay, in addition, the power transmitted in the small cells is reduced compared to the power transmitted in the larger cells, as it would require much less power to cover the cell compared to the large cells. In fact, the power has to be reduced by a factor of what? Look, P transmitted in small cell divided by P transmitted in the large cell will be R small cell over R large cell. R large cell rise to power what? Rise to power n. Now assume that n small, I mean the path loss exponent will be 4. At that time, we have the following ratio, okay? the power transmitted by the tower of the small cell is only 1/16 that of the what? That of the power transmitted by the tower of large cell. Okay, why? Look please. R small equals to what? Equals to 1/2R. Okay, يعني R over 2 over R. R will be cancelled with R. So we have 1/2 raised to power 4. It will be 1/16. Okay, so the ratio between the R, I mean power of the small cell to the power of the large cell will be 1/16. So 16 times we are going to reduce the power transmitted from the smaller cells. In addition to that, advantage of having higher network capacity due to the cell splitting, the reduced transmitted power, especially by the mobile phone, is another major advantage because it increases the battery life. I mean, to prolong the battery life of these mobile phones. The main disadvantage of the cell splitting, it requires what? The construction of new towers, which is what? Which is costly. Okay, so the cell splitting technique will enhances the capacity of the cellular communication system. Really we have another advantage, which is it will prolongs the battery life. But on the other hand, we have a disadvantage, which is what? Which is the cost. Why? Due to installing new towers. Again, means what? Means number of base stations will be increased. Well, this is about the cell splitting, and we have finished the topic of the cell splitting. Now we are going to talk about another important technique, which will be used for what? For enhancing the capacity of the cellular communication system, which is the sectoring. Now, in the previous lectures, we have talked about S over I, and I have told you that the limiting factor in the cellular communication system is what? Is the two things we have really, the bandwidth and what? And the interference. So, if you remember, we have talked about this relation, I mean S over I equals to square root 3n raised to n small over what? Over I naught. Okay. Now, in the cell sectoring, we are looking for what? We are looking for enhancing the signal to interference noise ratio. Look, please. In the previous lectures, we said that to increase the S over I, we have only one way, which is what? Which is increasing N. Increasing N will what? Will reduce the capacity of the system. Why? You are considering larger cells, so the frequency reuse, number of times the cluster is repeated, will be less than the, for example, in the case of smaller cluster sizes. So what we are going to do, look, please. We said that N depends upon what? Upon the environment, and it's constant. Okay, channel characteristics, and it will be constant. And in the urban area or the city centers, it will be 3 to 4, constant. Well, I naught, we said that I naught represents number of interfering cells where in the first tier, and it's constant again, and it equals to what? Equals to 6. N capital cannot be used for what? For enhancing the S over I. Why? It will reduces the system capacity. So what we are going to do? Really, cell sectoring will help us to what? To minimize I naught. I mean, instead of we have number of interfering cells equals to 6, in the case of 100-degree sectoring, it will be reduced, for example, to 2, and in the case of 60-degree sectoring, it will be reduced to 1. So the idea of cell sectoring will be what? To enhance S over I. Okay, After enhancing S over I, we can what? We can consider smaller cells. Okay. If we are going to enhance S over I, at that time we will be able to what? We will be able to use smaller cluster sizes. So the idea of the cell sectoring will what? Will reduces I naught. Okay, I naught. Now, without sectoring, I naught is 6. Okay, but with sectoring, I naught will be reduced. Of course, we have two cases. Case number one, when we are going to use a directional antenna of 120 degree, and in the second case, when we are going to use the directional antenna of 60 degree. Well, slideshow. Well, this technique increases the capacity via different strategy. In this method, a cell has same coverage space, but instead of using single omnidirectional antenna, I mean replacing the omnidirectional antenna by what? By directed antenna. That transmit in all three directions. Either 3 or 6 directional antennas are used such that each of these antennas provides coverage of to a sector of the hexagon. Now, with 3 directional antennas are used, 120-degree sectoring is achieved. Each antenna covers 120 degree, and when 6 directional antennas are used, 60-degree sectoring is achieved. Each antenna covers 60 degree. As you can see, this is an example for what? For 120-degree sectoring. Look, each cell will be divided into 3 sectors, S1, S2, and S3. And the whole number of channels which is assigned to this cell will be divided among what? Among the 3 sectors, S1, S2, and S3. This will be another example for what? For 6 antennas or 60-degree sectoring. Here we have 6 sectors in this example, S1, S2, S3, S4, S5, and S6. Okay, so here we have 6 sectors, and in this example, okay, the whole number of channels given to this cell will be divided among what? Among the 6 sectors. Now, by now we have some important notes we have to keep in our mind. Dividing the cells into sectors actually reduces the network capacity because channels allocated to a cell now are divided among different sectors. In the first hour, I have talked about the table of Erlang B, okay? And I have told you what? I told you that a group of 2 groups of 5 channels will provide less traffic intensity as what? At single group of 10 channels, okay? Now, the same story here. Look, in the case of 100 degree, say, assume that this cell is given 30 channels, okay? 30 channels. So the traffic intensity of 30 channels together will be greater than 3 groups of 10 channels, okay? This is, I'm talking about the trunking efficiency. Again, the same story here. If you are going to give this cell 30 channels, and then we are going to perform the sectoring, at that time, every sector has what? Has 5 channels. So 6 groups of 5 channels will provide less traffic intensity as what? A single group of 30 channels. This is the idea of trunking efficiency I have told. Well, in fact, handoff takes place when cell phone moves from one sector to another. Look, these are the disadvantages of what? Of the sectoring. Well, bad trunking efficiency, okay, and the handoff process is increased. Okay. The gain in the network capacity is achieved by what? By reducing the number of interfering co-channel cells. I mean I naught. Okay, I naught will be reduced. If the sectoring is done in a way that channels assigned to a particular sector are always at the same direction in different cells, it means group A of the channels assigned to the sector of the left to the tower in the cells and the group B of the channels is assigned to the sector at the top of the all cells, and so on. Each sector causes interference to the cells that are in its transmission angle only. Let's go to the figure to show you what I'm talking about. Look, please. Now here we have say cell A and 6 interfering cells in the first tier. Now what we are going to do, look, S2 is selected to the right, okay, for all cells, okay, for all interfering cells. We have selected the sector S2 to the right, and the sector S3 say to the left, and sector S1 to the top. Well, look at what will happen now. If you are going to study the interference on this S2, it will be affected by this cell and this cell only, these two cells, while the other will transmit their signals outside the sector 2 of this cell. So doing this process, I mean dividing the cell in this way or in this such a way, okay, what will lead? It will lead to what? In minimizing I naught from 6 to 2. Okay, so of course this will be dramatically increases the signal to interference noise ratio. Look, unlike the case of no sectoring, where 6 interfering cochannel cells from the first tier cochannel cell co-interference with 120-degree, sectoring 2 or 3 cochannel cells cause interference, and with the 60-degree, 1 or 2 cochannel cells cause interference. The number of cochannel interfering cells depend on the cluster shape and size. By having less than 6 interfering first tier cochannel cells causing interference, the SIR is increased for the same cluster size. This allows us to reduce the cluster size and achieve the same original SIR, which is directly increases the system or network capacity. Well, now we have explained for the 120-degree sectoring. Now, as seen in the figure below, the case of cluster size n equal to 4, only 2 of the 6 cochannel cells cause interference to the middle cell for the labeled S2 in the 120-degree sectoring. The cells with radiation sector colored red and green. Of course, I have talked about this figure. The other 4 cells, although are radiating at the same frequencies, cause no interference because the middle cell is not in their radiation angle. For the case of 60-degree sectoring, cell sectoring, only 1 cell causes interference, the cell with radiation sector colored in green. Look, please. Now, here we have the sector in the case of 120-degree sectoring. Look at the radiation direction of each cell. Okay, now if you are going to study the interference on this cell, I mean the red S2, okay, look, it's affected by the radiation of the green and radiation of the red. Well, in the case of 60-degree sectoring, again, I'm going to study the interference on red S2. Look, please. All radiation direction will not be affected, affects the S2, except what? Except the green one, okay? So I naught here becomes what? Becomes 1, which is a wonderful result. In addition to the reduced number of interfering towers that sectoring produces, the SIR is reduced due to another reason, since interfering tower always fall behind the tower if the sector is radiating to the right. Okay, example, the interfering cell must be what? To the left. Therefore, the worst case SIR occur when the mobile phone being served by that sector is located at a relatively far corner with respect to interfering. Now, this means that among 6 interfering cochannel cells in a non-sector system, the sector system gets rid of the worst interfering cells, okay, and this will enhances the system capacity. Okay, this is the case we talk about, and here we have a very important example, we are going to solve this example and another one, and we have a question at the end of chapter problems. Really, I prefer first of all to solve the problem of the end of chapter problem, and then I will go back to the example. Now, look at the book. Okay. Let's go to the end of chapter problems. Oh, sorry. No. We have a problem at the end of chapter problems. It's a very important problem, really. We have to solve it. Yes, this one, problem 3.5. Okay, problem 3.5. Look at the problem 3.5, please. A cellular service provider. Okay, a cellular service provider. Problem 3.5. A cellular service provider decides to use digital TDMA scheme, which can tolerate a signal to interference ratio of 15 dB. Okay, so S over I equals to 15 dB. Good. In the worst case, okay. Now find the optimal value of N. N capital is unknown for a omnidirectional antenna. Of course, when you talk about omnidirectional antenna, it means that what? It means that I not equal to 6. B with 120-degree sectoring, it means I not equal to 2. And C, 60-degree sectoring, it means that what? It means that I not becomes 1. Just look at the end of this problem, please. Look, should sectoring be used? Of course, based on your solution, okay, and finding out the results for this problem, you are going to decide either you are going to use the sectoring or not. Then if you are going to use the sectoring, which case are you going to use? 60-degree or 120-degree you are going to use? Assume a path loss exponent n small equal to what? Equal to 4. And consider what? And consider the trunking efficiency. Please, you have to see what I am going to do in this problem. This problem is very important problem. Why? In this problem, we are going to understand the operation of the cell sectoring. Let's go, of course, to the whiteboard to solve this problem in detail. Well, now we are going to start, with this problem. First of all, we are given the signal to noise ratio is equal to 15 dB. Okay, 15 dB. So first step, we are going to what? We are going to convert the 15 dB into what? Into ratio. Okay, so let's start. Now, as you know, when we talk about signal to noise ratio in dB, S over I, for example, in dB equals to 10 log S over I in ratio. So you have 15 equals to 10 log S over I. It means S over I in ratio will be 10 to power 1.5. Okay, 15 divided by 10, and anti-log, it will be 10 to power 1.5. Of course, it will be about 31.623. Okay, this is in ratio. Well, let's go to the what? To the first branch. I mean, omnidirectional antenna. I naught equals to 6 co-channel interfering cells. So S over I, I'm going to follow this formula. S over I, square root of 3n capital to n small over I naught. N small is equal to 4. So here we have 31.623 equals to 3n raised to power 1 over 2 raised to power 4 divided by what? Divided by 6. Okay, so here we have 6 multiplied by 31.628 equals to 3n all squared. Now we can solve for n, I mean square root for the both sides. So n capital will be about 4.59. Okay, 4.59. And as you know, according to the equation of the what? Of the n capital will be followed by I squared plus I by j plus j squared. Okay, n capital will be what? Will be 7. I'm not going to approximate the n capital to 4. Why? Approximating n capital to 4 means what? Means the S over I will be less than 15 dB. So we are going to approximate 4.59 to what? To 7 cells. Okay, so for branch A, n capital will be what? Will be 7 cells. Well, now let's go to the what? To the branch B. In branch B, we are going to follow the same equation. I mean, we have S over I equals to square root of 3n raised to n small over I naught. And in this time, we have the same value, 31.623 equals to what? Equals to, again, square root of 3n raised to power 4 divided by this time. In this time, I naught becomes 2. Okay, so we have 2 multiplied by 31.623 equals to what? Equals to 3n squared. Now, solving for n capital again, n will be what? Will be 2.65. As you know, if you are going to assume that I equal to 1 and j equal to 1, the cluster size and capital will be 3. So directly, I am going to assume that the cluster size n equals to 3 cells. Okay, now we have 3 cells only. Now, in the case of branch C, we have 60-degree sectoring. So I naught becomes 1. And we are going to follow the same equation. I mean S over I, square root of 3n to n small over I naught. And this will be 31.623 equals to 3n all squared divided by what? Divided by 1. In this time, again, solving for n capital will be about 1.87. Again, this will be approximated to 3 cells. Okay, I mean n capital equal to 3. Now this will be, we have reached to the what? To the important point in this problem, which is what we are talking about what? About, are we going to use the sectoring or not? Now you have to answer this question. Are you going to use the sectoring or not? Without sectoring, the cluster size is equal to 7. With sectoring, the cluster size is equal to 3. Now, which one do you prefer? Which one do you prefer? يا جماعة, we have 3 cases. Case number 1, the cluster size is equal to 7. I mean with omnidirectional antenna with no sectoring. With sectoring 120 degree, the cluster size is equal to 3. And the cluster with the sectoring of 60 degree, the cluster size again is equal to 3. Now, are you going to consider the sectoring or not? Someone may answer, huh? هل يا جماعة؟ Are you out of coverage area? صفا شارت موجودين؟ Yeah. Huh? Are, what we are going to do? Are we going to consider sectoring or not? Well, okay. Really, sectoring will be used. Why? Without sectoring, the cluster size is 7. While using the sectoring, cluster size n equal to 3. So this will enhances the system capacity. The second question, if you are going to consider the sectoring, now you have 2 kinds of sectoring, 120 degree and 60 degree. Which one do you prefer? Really, 60 degree and 120 degree leads to the same cluster size. Okay, so we are going what? We are going to utilize the clusters, the sectoring of 120 degree. Why? Because 120 degree will provide better trunking efficiency as compared with what? As compared with 60 degree sectoring. Okay, this will be the solution of this problem. I mean, problem 3.5 is a very important problem. Well, now let's go back to the example. In this example, it's a very simple example, really. A cellular system uses a frequency reuse factor of n equal to 4, n equal to 4, I equal to 0, j equal to 2. It means if the path loss exponent n equal to 4 and cell radius r equal to 5 kilometer, find in dB the following quantities. The SIR for the system with no sectoring, of course, I naught will be 6. SIR 120 degree cell sectoring, okay, I naught will be 2, and here I naught will be 1. In this example, the S over I is missing, so directly you can use the formula of the S over I equal to square root of 3 n to power n small over I naught. Merely you are going to change the value of I naught in each step and recalculate the equation to determine what S over I, and don't forget to determine the value in dB. After finding the value, you are going to calculate this value, I mean 10 log signal to noise ratio. This is about the equation, the lecture of what? Of increasing or improving the system capacity of the cellular communication system by using the cell splitting and cell sectoring. In the next week, inshallah, we are going to talk about a new topic, which is the separate spectrum And we are going to talk about two kinds of separate spectrum. I mean the direct sequence and the frequency hopping separate spectrum. Do you have any questions or not? Do you have any questions?
That's positive.
نخش در سرچاوا برا. Okay, so see you next week inshallah, and goodbye.